G'day guys, you're back with MiracleMAX. Today we're looking at a Hisense TV that's been caught out in a lightning storm and now she's kaput. What's wrong with it? I don't know. Let's have a look together. For those of you who are remotely interested, well, you can't be because this one doesn't have a remote with it currently. It is a model 50N4, which means it's a 50-inch screen and it's a smart TV. So what's our first step? Let's hook up the power and see if we have a standby light. So I've turned on the power and no standby light. Well, I didn't expect it to be easy. Let's pull it apart and have a look inside. Look, I'm the first to admit that I occasionally take on maybe too many projects. I'm sure that Mrs. Miracle would agree with that. That's why I'm not in the lab at the moment. There's just no room in there and I'm working on the kitchen table, in fact. Love you. Hey, it's not too bad to pull off this back section here. It's just a series of screws. All of them are machine threaded screws apart from two. And the two self-tappers are located here and here. So now that all those screws are removed, it's just a matter of wiggling this plastic section off and removing that. That exposes all the boards that we need to look at. The board on the left hand side is our power board. Now this is where I'll be focusing most of my attention simply because we don't have a standby light. If I had a standby light, I'd be looking perhaps either at the power supply, the power board that is, or the main board. And this is our main board on the right hand side. I've searched for a service manual online but couldn't find one, but fortunately they've been kind enough to put the series of voltages necessary to power up our main board. So we could test there or we could start right back at the beginning. As mentioned, this was affected after a lightning strike, so I'm not going to head up the other end of the power board but right at the beginning. Why is that? It's up this end that we have the protection circuit. We have a fuse here, we have a varistor here, and I believe that might be a secondary varistor over there. They're the ones that I want to check for starters before I start searching elsewhere. Before I start poking and prodding around there, I want to make sure that it's safe to work on. So what I'm going to do is check my main filter capacitors here to make sure that they're drained of voltage, and if not, then I need to do something about that. Let's just have a look at what we have here. We've got pretty much no voltage, that's good. This little fella, probably the same, usually in parallel. Okay, so now I know that that's safe to work on. If it still had voltage, I would use something like this little tool that I've made. Basically, it has a resistor in here, or a couple of resistors, and all I do is I short across those two terminals there to drain away any voltage. I'll do that one, and of course I would do that one, and recheck it with my multimeter. But I know that it's safe to work on. So, next step, to have a look at the varistor. So to check my varistor, it needs to have very high resistance across those two sections there. As you can see, 7 ohm. That's next to nothing. It should be in the mega ohm range. I'm also going to check this little fella over here and see what he's doing. That's more of what it should be. In the mega range, you can see that there. But this little fella here is possibly fried. I'm going to pull off the board and check this fuse here and maybe these diodes, etc., and see what they're like. I actually stand corrected, guys. These are not diodes, they're actual fuses, bead fuses they're called. So let's check those ones, and of course they should have continuity across them. I'm in the ohm range and you can see that's perfect. That one there is, let's have a look. There we go, that's perfect as well. I see that there's another one over here, although that's listed as an L. That might be an inductor. That should be okay. I think they're inductors as well. Well, I think this has bigger issues than just a blown varistor and fuse. I'll check that fuse. Good protection circuit, guys. Didn't even blow the fuse. It's taken out an inductor there by the looks of things. So if we flip him over to that side, you can see that that's where the inductor is. I'll need to pop that off and have a look underneath and find out what exactly is there. But that looks like the inductor there. Perhaps there's something underneath there. It's blown a track or something perhaps. I'll clean that up with some alcohol and just see what's meant to be there, what's missing, or if something underneath the inductor is affected. So yes, I'd say the inductor's given up the ghost. Not only that, she's blown the bum out of the track itself, so I'm going to have to bypass that track, perhaps put a wire between there and there, whoops, there and there, to get the thing up and running again. And I'm going to pull off this inductor and have a look, but I'd say she's knackered. I'd say it's blown the inductor clean apart. The only problem is trying to get parts for it. That may be an issue. Before I go any further, I'd like to do a few other basic checks, including this MOSFET, this MOSFET. I've checked my bridge rectifier, and that's fine. I'd like to check these diodes as well. So to check our MOSFET, this is an N channel, I believe. If we go one way, it should have a certain reading. If we go across there, it should have a certain reading, and then going backwards, we should have a different reading, which we do, and which we do. And between there and there, that's okay as far as I'm concerned. We'll check this one over here, 0.5, 1.1. If we go backwards, 0.7, and across there. I'm happy with those for the moment. So to sum up briefly, parts that we need definitely. There might be other parts as we put them back together. We need a varistor, we need an inductor. This has been blown out, and that's not unusual in a lightning strike. That's what they're designed for. The inductor, on the other hand, has taken the full brunt of all that excess voltage coming through. Didn't like it, decided to give up the ghost. These diodes appear to be okay. Bridge rectifier is okay, and these MOSFETs both here and here are okay. So look, I'm going to order this part and see how we go after that. Another thing I wanted to check before I went any further is this burn mark here. Now this is a plastic insulator, and I just wanted to make sure that there's no damage being done to the actual backing of the TV, and that looks fine itself. I can't see any issues there, and it's not through the other side of that plastic insulator. I've just had a bit more of a think about this particular inductor here. Now if this was blown, it looks like it's a two-piece inductor. A section here and a section here, and it's identical to this fella over here. Now I've done testing on this one over here, and it's identical to this one over here. Now if this had blown its backside out, in other words it had taken out the wire through here, it should be an open circuit, shouldn't it? So these wires here, if you can see them there, that little wire there and that wire there, if it had blown the backside out of that wire, then there should be no continuity between that point and that point. And yet, as you can see, as I go between this inductor, should be about 0.8, which it is, over to this side, I started unsoldering it. That's 0.8 over there. And if we go over to this inductor over here, which is over that side, this fella over here, and we have a look at, where is it? Let's get your head sorted there, Max. All right, that fella over here, that should be 0.8 again. Yeah, bad connection there, I'm believing. There we go. And if I go over to this side here, should be 0.8 again. All right, so look, I'm starting to rethink my diagnosis there. I'm actually going to replace that varistor, repair this here, make sure all these solder joints are in good nick, and see what it does. Look, what can it do? Blow up again? I guess it can. But look, that track is the main problem, because the inductor actually starts, as you can see, between here, and if the wire was actually blown, there'd be a dark mark around here, not through the centre like here. So to me it looks like just the tracking has let loose. Maybe it was the thinnest point there, the weakest link, and it's let loose. But I can't see that the inductor is damaged at all. So look, there's no dark marks. There's continuity between the two sections of the inductor. As I said, it's a two-part inductor, and it's okay from here to here. So honestly, I'm going to change this varistor and give it a burl. As you can see, I've put in a bypass wire, and what that does is bypass this track that comes along through here, which had an open circuit through here, and I just want to check and make sure I've got good continuity there, and I have. No probs. Well, I've already checked this inductor, this one here that blew its backside out, and I had to bypass the track there, with a multimeter. Really, that's not the best method to check an inductor. Something like this blue ring tester is ideal for testing purposes. It's not that hard to use, quite easy in fact. If we look on this side of the inductor, we can see that the wire goes from here to here, and there's a second one over from here to here. So if we turn it up the other way, it's these 2 points here. That one there, that's one set of wires. and of course across here to here is our second set of wires. I've just switched it around to make it easier for you guys to see. So if we put one contact point there and the other contact point there, we should have all rings complete. As you can see, it's in the green, all the LEDs are lit. So that shows that we're getting a continual ringing effect as this pumps perhaps an AC signal through the wire and oscillates it so that it gets a ringing effect. Let's have a look at the other one, which will be this one over here, that one there, and I assume that one there. And as you can see, once again, we have a good ringing effect. All green LEDs are lit. So I'm very happy with this. This inductor is clearly in good condition and I can move on. Look, I'm the first guy to stick up his hand and say that he doesn't know everything. I'm constantly studying, constantly learning, constantly doing research. So books like this one by Justine Yong, Testing Electronic Components, is fantastic. And of course, me, being me, I've studied it long and hard. You know, there's highlighted sections there, out with the old highlighter. I've gone nuts, of course, to study it and make sure that I've got it clear in my head. Hey look, I've been caught out. This fella over here is not a varistor. He is in fact a NTC thermistor, which tests differently from a varistor. That's this bloke over here, a varistor. This fella over here should have low resistance at room temperature. This fella here should have very, very high resistance at room temperature. So let's check them now that we have more information and the correct testing procedures, and see if they are okay or not. So remember, this thermistor should have a low resistance at room temperature, which it has, and this varistor should have high resistance at room temperature, which it does. It's in the mega range there. Look, both those protection fellas are okay. The fuse is okay. Look, I can't actually see anything wrong with it apart from the fact that it burnt out that track, and hopefully now that I've repaired this track, it should be up and running. Oh, I don't know. Let's give it a whirl, shall we? Yes, it was wishful thinking on my part to think that one little burnt track could have solved the issue. But hey, look, I think my protection circuit, now keep in mind that this is live, my protection circuit is okay. I also think that my rectifier, my bridge rectifier, is okay. Reason being is if I check at my filter capacitors, you can see there that I've got 300 odd volts, 340 volts. I believe from this area down, it's fine. The next thing that I need to check is my transformers and make sure that they are being chopped by my MOSFETs here and here, so that the transformer can give an oscillation across to my low voltage side. At this point, I think that my high voltage side is okay, apart from I need to check my transformers, my optocouplers over this side as well. I believe that each of these transformers will represent a different voltage, so I need to make sure, perhaps checking over here where you can see the voltages are listed, and see what voltages I have available. And if I don't, obviously I've got to chase that particular rail. I've just been doing some very basic checks, for instance diodes, transistors, etc., MOSFETs, and of course making sure that my capacitors are in good condition. Now this is the high voltage side of our power supply. This is our low voltage side of our power supply. If we just zoom in on these fellas, they're called optocouplers, and they're sitting side by side. These little guys are identical, and they're classified as an L1835, 817, 8. So really their readings should be identical. They're called optocouplers. They're basically like a photodiode with a photo receiver on the other side enclosed in there, so that an LED flashes and the receiver picks it up and then transfers voltage through, or allows voltage to go through. So in theory, the readings on my multimeter should be identical, shouldn't they? The TV set is turned off at the moment, and I always leave the plug in front of me so that I can see that I've powered it down. I've got my multimeter in the diode range, and I'm just going to check either side of my optocoupler there on this side. That's saying there's no continuity. If we go the opposite side, it should have some sort of reading, which it does. And if we go to the bottom, that should have something fairly similar, I would imagine. I can get in there. We've got one. We come back the other way, turn our leads around, and we've got no reading. That's excellent. That's good news. Let's go to the next one, the one sitting side by side with it. Ew, that's not a good sign. Let's go opposite. Ew, not happy Jan. Alright, so there's a bit of a fail there and a fail there. Now look, either it's the optocoupler itself or it could be a short creating that across there. So I need to remove that little optocoupler and then check that off board, and if that's okay off board, then I need to find out why I've got this short across here. That obviously won't start up the set if this thing is shorted out. Now that I've got my little optocoupler off the board, it's important to check components off board. It gives you more of an accurate reading, and obviously it's good to test components independent of the actual circuit. So we put him onto the diode setting. An optocoupler is basically an infrared LED on one side, and that shines a light onto a phototransistor on the other side, therefore completing the circuit while being electrically isolated. Therefore they are independent of one another. This side of the circuit, which is usually the high side, and this side is the low side, or vice versa. Okay, so let's just check this optocoupler and see if it's any good. As you can see, what I've done is stick it onto a piece of cardboard. It's a lot easier than sliding the whole thing around on my little workbench here. So we're looking for continuity one way only. Okay, so that's not one way. And do we have a reading the other way? So that's clearly open. There's no connection there whatsoever. Let's turn him around the other way. So that side is not happy Jan, and the other side here is, that's got a dead short right there, guys. So yes, that's definitely faulty. So what I'd like to do now is actually check the circuit that it's attached to and make sure that there's no dead shorts across that circuit, which in fact created that fault. Was it just the lightning strike that fritzed it, or is there a fault further on? You can see that this is my other opto, and I've checked that. I might just double check that again just to show you what it should look like. We should have a reading one way, which we do, and a different reading the other way, or classified as outer limits, which is good. And this side should have something similar, so it should be outer limits there, and the other side should have about 0.6, something along those lines, whatever it is. You can see there's a difference between the two, so that one is okay. The other fella is not. But what I do want to check is there any shorts between this area here and this track through here? Now, if we go like this, you can see that it appears to be a dead short, but I got caught by this, I must admit. I travelled further down here and found that this little tiny capacitor down here appeared to be giving a dead short. I had a look on the net for testing procedures to find out if this capacitor was faulty or not, this little surface mount device just down here, and they suggested that you stick this on the sound little buzzer there and you check all your capacitors and see if they are faulty or not. Now, where are my caps? There's one there. That's not buzzing, not buzzing, not buzzing, but that one there is buzzing. That gives the impression that it's faulty, okay? Now, just because these leads have continuity and you get the buzzer happening, that doesn't necessarily mean that there's a dead short. You could put a resistor across here and it will still buzz. I think you can get it up to about 100 ohm and it will still buzz. Here's an example, okay? We have a resistor here of 39 ohm, as you can see there, and have a listen. We got nothing, okay? Well, you're saying, well, Max, that doesn't prove anything, does it? Okay, let's try 15 ohm and see what happens. Okay, so at 15 ohm, which is a reasonable amount of resistance, this is still giving the impression that there's a dead short. So just because you find a capacitor or something that has a buzzer attached to it, you can see that's got 0.9, that doesn't have a dead short. I'll show you just a few other testing procedures that were shown to me to indicate that that capacitor should be okay. So by using an actual capacitance meter, as I have here, it should give me a reading of somewhere between 1 and 10 microfarads, and that's pretty much spot on 10 microfarads there, guys. It's building a little bit, but it's hanging around the 10 mark there, which is pretty good. So I reckon that that's okay. So after all that testing, I'm just going to replace that little optocoupler there. I'm happy with my repair up over here, and put it back together, and hopefully we've got it sorted. Won't know until we hook it up. The only problem with one component being shorted out or opened is that it affects other circuits. So while I haven't been able to find a schematic for the actual TV itself, the Hisense TV, what I have been able to find is a schematic for the power supply, and I've done that by means of this little number down here. That fella there, which ends in 5687. I was able to look online and find a schematic just for the power supply board. And that there gives you a bit of an idea of what we're looking for, but the area that I'm looking for is this optocoupler right here. This is the one that's blown its backside out, so this is the circuit that I want to focus on. I've been able to zoom in further and make this area a lot clearer than it was before. So this is the optocoupler, the N891, that has failed. It opens circuits on the phototransistor side of things, so obviously there's something over this side of the circuit that is creating the problem. From the testing that I've done so far, I actually lifted up the legs of this optocoupler just then to check it, and I have got ground on both, or I've got continuity between both sides there. It shouldn't have continuity when the opto is lifted because that's the completing of the circuit. So obviously, and I've got a very good continuity, so it's down to about 1 ohm, something along those lines. So what I'm going to do is lift the little IC over here, which is a 1271A, and that is a pulse width modulated controller. So I'm going to lift the legs off of that fella and see if we can get rid of this continuity between this area over here. I don't believe there should be continuity. That's a feedback circuit going back there, comes across, there's a cap across there, but that cap, I might have to lift a leg on that cap as well to see if there's a short through there. We'll see how we go with that. So this is the circuit that we're looking at. It's on the back of the board. The little opto is over here. That's the one that's damaged, and you can see I've pulled the legs out of that. Now I want to trace this back. I will remove one leg of this little cap and see if that gets rid of the cross or the continuity across here. If not, I'll lift up the IC and see if that gets rid of the continuity across the phototransistor there. Then that would indicate that there's possibly a short inside of here. You can see I've lifted the little leg or one side of the cap here, so there's no continuity between there and there, but I'm still getting the same reading. I'll show you. So if I go across either side of the phototransistor, you can see that I'm still getting like 1.4, 1.3 ohm, which it shouldn't be. Otherwise, what's the point of having a transistor in there? So I think the little IC is for snookered. I spent quite a bit of time making sure that I could get the little IC off. I put on some flux, I put on some new solder, gently lifted it up, put a big puddle of solder so all the legs would lift up at once. Major problem, Max, was I took off the wrong one. Took off this one over here rather than this fella over here. Idiot. But finally I got the fella off. There he is there. And let's have a look at the resistance across that optocoupler now. Is there a short across there? Let's have a look. Remember before we had about 1.4 ohms, something along those lines anyway, and that's pretty close to a dead short. Let's have a look at what we got now. So we've got an open circuit, which is excellent, which means that that IC probably has an internal short. You can't blame the fella for getting like millions of volts from a lightning strike shoved into it. Anyway, I'll order another one and see what we can do. This is all a bit new to me. I'm used to doing my work under a magnifying glass, but I've had this microscope for a little while, but haven't really put it to use, but I thought I'd give it a shot today. I'm just about to put that little chip in place, so let's chuck some flux in there and make sure that we can put good contact points there. Make sure that we do a good job. And now, hopefully we can get our chip into place. Now, I've got to make sure I put it in the right way around, of course. Now, I've cleaned all my solder points, etc. Put in new solder. Just see if we can pop down one of the legs. Try this one here for starters. Okay, just need to readjust it a fraction. That side coming around a touch. Bit of fiddly work here, guys. It's hard for me to do this. Like I said, it's new to me, so I'm just getting used to it. That looks pretty right there. So we need to do this leg just here. There we go. There's a bit of a close-up of the work so far. I'm happy that there's no legs that are joined over here and here, and over the other side there appears to be no bridging. So last time we tested this across the Optocoupler, once that was removed, I think we had about 1.2, 1.3 ohms, and clearly that was no good. So let's test it with a new chip and see what we're reading. There we go, 71 kilo ohms, 81 kilo ohms, something along those lines. And so yeah, I'm happy with that. That's definitely better than 1.2 ohms, isn't it? Pop our Optocoupler in and fingers crossed we've got it sorted. Optocoupler's in place now, and all I have to do is clean up a bit of the flux material. So give them a bit of a blast there and make sure that I tidy them up properly. And I've checked the connections, they appear to be okay, so that's all good. I'll clean up the chip area as well and double check all my work. Clean off all that flux residue. And that should dry off shortly. I've just put my power board back into place, and I'm not sure if you can see what I can see. Might even have to turn this light out. See the little light there? Our standby light. That's good news. That's encouraging. Let's go around the front, hit it with the remote control and see what happens. Okay, moment of truth. Let's hit the big red button on the remote. Oh, look at that. Well, that's a good sign. It's a shock to me that I fixed it. I'll have to hook it up to an aerial, etc. But that's certainly good news. There's a backlight. There we go. We've got the TV just waiting. No signal there, no problems. That's a little bit out of focus for you. Sorry about that. Oh, there we go. That's not bad considering it was struck by lightning or affected by a lightning strike, and able to get it up and running. It's a good feeling to get it up and running like that.
You know what? In all my excitement, I actually forgot to record the TV being operational, but as you can see, Netflix is working, the TV channels are working just fine, movies, etc, etc, and I also stuck in a DVD and that thing worked just fine, so there was no problems whatsoever. Not bad considering that this little bad boy had been struck by lightning or affected by a lightning strike.
Well guys, it's a great feeling to be able to keep yet another TV out of landfill. At this point, I'd like to give a great shout out to Justine Yong, who gave me some great diagnostic suggestions to come to this successful conclusion and repair this TV. I hope you enjoyed the video today, and if you haven't already, please subscribe to the channel. Give it a like and feel free to comment down below. But of course, don't forget about that notification bell. You don't want to miss any future videos, do you? Nah, of course not. So until next time guys, this is MiracleMAX signing off. I will catch you later.